Have you ever wondered how many alien civilizations might exist in our galaxy? This is a question that has intrigued humans for centuries, and one that astrophysicist Frank Drake sought to answer with his now famous equation. The Drake equation, named after its creator, is not so much a solid mathematical formula as it is a thought experiment, a way to frame the countless unknown variables that come into play when we ponder the existence of alien civilizations. It's a tool that helps us understand the factors that might contribute to the presence of life beyond Earth. Picture this. Our galaxy, the Milky Way, is vast, home to hundreds of billions of stars. Around many of these stars orbit planets, and some of these planets could potentially host life. But how many? And how many of these life forms have developed into intelligent civilizations capable of communicating across the cosmos? The Drake equation doesn't give us a definitive answer. Instead, it provides a framework to consider the probability. It's made up of several factors, each representing a stage in the potential development of alien civilizations. These include the rate of star formation in our galaxy, the fraction of those stars with planetary systems, the number of planets that could potentially support life, and so on. The beauty of the Drake equation is its flexibility. As our understanding of the universe evolves, so too can the values we assign to each of these factors. And while the equation may not provide a precise number, it does offer a way to organize our ignorance, to quantify our uncertainty, and to fuel our curiosity. So, as we stand on the brink of the unknown, the Drake equation serves as a compass, guiding our search for life in the cosmos. It reminds us of the vastness of our galaxy and the multitude of possibilities it holds. So let's break down the Drake equation and understand each factor. The first variable in the Drake equation is r*, the rate of formation of stars in our galaxy. Now, this is not just about counting the stars in the night sky. It's about understanding how often new stars are born. Why is this important, you may ask? Well, each new star represents a potential system where life could develop. The higher the rate of star formation, the more chances we have for life to emerge somewhere out there. So, how do we estimate r* then? Astronomers observe various regions of the galaxy, especially those dense gaseous nebulae where stars are known to form. By studying these regions over time, they can estimate how many stars are born in our galaxy each year. But stars alone are not enough. The next part of the Drake equation is Fp, the fraction of those stars that have planetary systems. After all, we're not just looking for stars, we're looking for potential homes for life. And as far as we know, life requires a planet or a moon, a solid surface where chemical reactions can take place and life can evolve. With the advent of powerful telescopes and satellite technology, we've discovered thousands of exoplanets orbiting distant stars, proving that planets are not a rarity in the universe. So, Ikis FPE is not a small number. However, not every planet can host life. They need to be in the right place, often referred to as the Goldilocks zone, where conditions are just right, not too hot, not too cold, but just right for liquid water to exist. So in the Drake equation, r* and Fp together give us a rough estimate of the number of planets in our galaxy that could potentially host life. They provide a starting point, a baseline from which we can explore the possibility of existence beyond Earth. These two variables set the stage for the potential existence of life elsewhere in the galaxy, but they are just the beginning. In our next discussion, we'll delve deeper into the Drake equation, exploring the variables that deal with life itself, its evolution, and its ability to communicate across the cosmic void. Moving forward, we come to Ni, the number of planets per solar system with an environment suitable for life. This is a crucial variable in the Drake equation, and it's also where things start to get a little tricky. Our understanding of what constitutes a suitable environment for life has evolved significantly over time. Once, we believed that only Earth-like planets could harbor life, but as we've learned more about extremophiles, organisms that thrive in extreme conditions here on Earth, our definition of suitability has expanded. Now we believe that life could exist in a wider range of environments, from the icy moons of Jupiter to the potentially habitable exoplanets we're discovering with increasing frequency. This broadened perspective means that Na, the number of suitable planets, could be higher than we once thought. But it's still a variable with a lot of uncertainty. We don't yet know how common these potentially habitable environments are, or what proportion of them actually host life. That brings us to FLE, the fraction of suitable planets on which life actually appears. This is another challenging factor to estimate. We only have one known example of a planet with life our own, and so it's difficult to make broad generalizations. However, we can look to the fossil record on Earth for some clues. Life on our planet appeared relatively quickly after conditions became suitable, suggesting that if the conditions are right, life may be a common outcome. But again, without more examples, it's hard to be certain. These variables, Ni and Fl, help us quantify the potential for life in our galaxy, but they are also reminders of how much we still have to learn about our universe. As we continue to explore and discover, these estimates could change, shifting our understanding of our place in the cosmos. At this point, we have considered the factors that could lead to the emergence of life. But what about intelligent life? The next variable, Phi, represents the fraction of life that evolves into intelligent beings. This is where the Drake equation delves into the realm of speculation. We've only got one example to work with, our own planet Earth. The emergence of intelligent life here could be a freak accident, or perhaps it's a natural progression given the right conditions. What we can say is that Phi is somewhere between 0 and 1. If Phi is close to 1, it suggests that once life gets started, it's almost inevitable that intelligent life will eventually evolve. If it's close to 0, then we might be very alone in the universe. Moving forward, we encounter Fc, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. This is another speculative term, but it's crucial. It's not enough for a civilization to be intelligent. They also have to be technologically advanced enough to send signals into space that we could detect. And not just any technology will do. They need to have developed radio or laser technology or something equivalent, which can send information across the vast distances of space. Again, we have only one example to work with, us. We've been leaking radio waves into space for about a century, and in that cosmic blink of an eye, anyone within 100 light years who is listening in the right way could potentially know we're here. But here's the thing. Even if a civilization has the right technology, they have to choose to use it. And they have to use it in a way that we can detect. That's what EFC represents. If EFC is 1, then every civilization that develops to our level of technology chooses to broadcast their existence into space. If it's 0, then none do. Finally, we need to consider how long these civilizations can communicate. This is the final term in the Drake equation, denoted as L, and it's the subject of our next discussion, so stay tuned. The last variable, L, stands for the length of time for which such civilizations can release detectable signals. It's a reminder that our search for extraterrestrial communication is a race against time. Civilizations could rise and fall in the blink of cosmic time, and our window to catch their signals might be incredibly small. The Drake equation as a whole is a powerful tool. It breaks down the daunting task of estimating the number of civilizations in our galaxy into manageable parts. Each variable highlights a key aspect of the process, from the formation of stars to the development of life and technology. By providing a structured approach, the Drake equation allows us to make educated guesses about extraterrestrial civilizations. It sparks scientific curiosity and drives our search for life beyond Earth. So, while the variables might be uncertain, their importance cannot be understated. Though we may not yet have the answers, the Drake equation provides a framework for us to continue to explore the fascinating question of extraterrestrial life.